Hello again, Lou McIntyre here to talk to you some more about the special theory of relativity. Let's get into it. In this video, we will talk about making radar measurements of relativistic moving objects and derive the Lorentz transform from the radar measurement. First, we need to look at how a radar makes a measurement. There are two kinds of radars, pulse and Doppler. Pulse radar emits pulses of a certain radio frequency with a particular width and repetition rate and determines the location of an object by comparing the time of pulse transmission and the time of receipt of its reflection by the object. Most radars are of the pulse type. We're not going to be concerned with frequency, pulse width, and pulse repetition rate, except to note that all of these parameters are intervals of time determined by the radar's clock and will undergo Doppler shift due to the reflecting object's velocity. Doppler radar emits continuous radio frequency energy at a fixed frequency and compares the frequency of the reflected wave to determine the object's velocity due to Doppler shift. An example of this is the police officer's speed gun. We're not going to be concerned with Doppler radar. Let's see how radar locates an object. At the time of transmission, the radar emits a pulse which travels outward at the speed of light, covering equal units of time and distance. After some time, the radar pulse encounters an object and is reflected back to the source, arriving at the time of receipt. Distance is calculated by dividing the difference between time of receipt and time of transmission by 2. The time of reflection is equal to the sum of time of receipt plus the time of transmission divided by 2. Radars do not usually calculate time, since the difference terrestrially between time of transmission and receipt is a millisecond or less, and the movement of a terrestrial object in this interval is minuscule. This is not going to be the case with our objects traveling at significant fractions of the speed of light. Here we see that for a pulse transmitted at time equal to 3 and received back at time equal to 6, the reflection occurred at time 4.5 at a distance of 1.5. It isn't necessary to use just radar for measurement. For objects moving at relativistic speeds, the delay is long enough that a simple radio transmission and the reply will give the same results. Now let's see how radar will locate an object moving at relativistic speeds. Let's set this up as a little anthropomorphic problem that can involve two-way communications as well as radar. Let's have S1 be Sam in mission control on Earth. Sally is going to be S0 in her spaceship, leaving Earth at noon. Sam has mapped out her trajectory as X1 equal to VT1. At 3 in the afternoon, Sam's radar sends out a pulse, which comes back at 9 p.m. Sam determines that Sally was at 3 light hours distance at 6 p.m., right on her world line. Where is the relativity here? There is none, because all the clocks and rulers belong to S1. Therefore, Sam, the earthbound observer, sees the ship moving with respect to the radar beam. If there is a fixed point on his ruler for example, a stationary space station located at 3 light hours out, he will see the two returns merge at 6 p.m. because the pulse reflected by the spaceship and that reflected by the space station will arrive simultaneously at 9 p.m. Sam has no other place to put Sally except on the pre-planned x1 equal vt1 trajectory. But also at 3 p.m., Sam called Sally to check on her status and asked her what her instruments told her. He also called the space station to ask where she was. Both replies came back also at 9 p.m. The space station confirmed that she was just passing by at 6 p.m. However, Sally reported that she got the message at 12 minutes past 5. Her instruments told her she had covered 2.6 light hours, right on the money, at half the speed of light. But she was already at the space station, just 86% of the 3 light hours distance it was supposed to be. What is going on? Why is her clock running just 86% of Sam's and her instruments showing just 86% of the distance that Sam has measured her traveling? The difference is that we are now comparing measurements made using Sam's clocks and ruler with those made by Sally's. Let's set up Sally's timeline on the 30-degree radial, corresponding to her relative velocity of half the speed of light, and her x0 axis normal to it. What is the difference between the x1 equal vt1 trajectory in blue and her timeline in red? The x1 equal vt1 trajectory is the locus of successive measurements of Sally's position by Sam using his clock and ruler, what Hermann Minkowski called the world line. The world line is separated from Sam's timeline by the Minkowski angle mu. Mu in this case is 26.5 degrees, the tangent of which equals v over c. The red CT0 is Sally's timeline, the locus of successive ticks of her clock, separated from Sam's timeline by the Brem angle beta, 30 degrees, the sine of which is v over c. Let's see when Sam's 3 p.m. transmission actually reached Sally by her clock. Sam's transmissions are Doppler shifted. Equal units of space in the reference frame of origination to equal units of time in reference frame of receipt, reaching Sally at 5:12 p.m. by her clock, more precisely 5.196 hours after takeoff. This is really not her clock running slow. It's when the signals actually got there. The Doppler shift between Sam and the stationary space station is 3 light hours away, is unity, and only transit time of 3 hours out and back, while the signals to Sally undergo a Doppler shift of 1.732 due to her velocity of half light speed. But how does that square with her reply arriving simultaneously with that from the space station? Her reply will be Doppler shifted along the return path, equal units of space in her reference frame and equal units of time in Sam's, to arrive at 9 p.m. simultaneously with the radar return and reply from the space station. Sam's query to Sally at 3 p.m. and his radar signal both undergo 2 Doppler shifts, one from his query to her and the second from her reply to his receipt at 9 p.m. And the product of those 2 relativistic Doppler shifts is exactly the same as the transit time to the stationary space station at 3 light hours, marking that point on his ruler. Nobody's clocks and rulers were affected by relative velocity, as both reference frames use the same scale for both. They're just rotated with respect to each other. And they have to be unaffected because clocks are governed by the laws of physics. And the first postulate of Einstein's special theory is that the laws of physics are invariant in all inertial frames of reference. Rulers, in turn, define the law of physics, so they too must be invariant. And Sally will measure Sam's time of transmission occurring by her clock at 3.464 hours after takeoff at a distance of 1.732 light hours, receding from her at half the speed of light. Her measured time and distance to Sam add up to her time of receipt at 5.196 hours after takeoff. Thus, both reference frames measured the same speed of light, with the other appearing to move with respect to light, satisfying the second postulate of the second special theory that both measure the same speed of light. And they both measure each other's clocks and ruler, slower and shorter, respectively. Have you ever seen a graphic capturing in simple terms how those two measurements, seemingly in conflict, are both satisfied? Now let's derive the complete Lorentz transform from the radar measurement. Sam wants to compare Sally's ruler with his. To do this, they must make the measurement of the same object at the same time. Otherwise, the two measurements cannot be compared. So, at 1.732 hours after takeoff, Sam asks Sally to locate a slow-moving asteroid. Sally gets this message at 3 p.m. and begins looking for it. Sally gets a radar return from the asteroid at 7 p.m. and determines that it was 2 light hours away at 5 p.m. Sally reports this measurement to Sam, who receives her measurement at 12.12 hours after takeoff, simultaneously with his own radar return. Sam locates the asteroid at 5.19 light hours out, 6.92 hours after takeoff. Subtracting Sally's position on her world line at x1 equal to 3.46 from his measurement to the asteroid of 5.19 units of distance, he determines that the asteroid was 1.732 ahead of her, 86% of her measured distance of 2. But why does light seem to change direction in the two reference frames? It does not. Light is not a beam, but an expanding sphere anchored on the point of emission, remaining centered around the emitter. From Sam's time of transmission, Sam's request becomes tangent to Sally's timeline at CT0T. From CT0T, her radar signal expands, reflecting off of the asteroid and returning to her at time 7. And her report to Sam expands from CT0T, becoming tangent to Sam's timeline at CT1R. Sam's radar measurement has continued to expand from CT1T, reflecting off of the asteroid at CT1X1 and returning to his timeline at CT1R simultaneous with Sally's reply. Now let's do the math. First, we calculate Sam's time of transmission, CT1, as the inverse Doppler shift of Sally's time of transmission, CT10T, CT0T, expressed in terms of CT0 and X0. Rearranging this, we find that CT1T is the difference between the Lorentz transform for CT0 and that of X0. Next, we calculate Sam's time of receipt, CT1R, as the forward Doppler shift of Sally's time of receipt, also expressed in terms of CT0 and X0, and find that it is the sum of the Lorentz transform for CT0 and X0. And applying the radar equation to these two terms, we find that Doppler shifting Sally's synchronized radar measurement back to Sam's time of transmission and receipt yields the Lorentz transform. Quaderat demonstratum. Thus, it has been shown. So in summary, the radar equation uses light to locate an object in the radar's space and time. Velocity need not be known, but can be determined by two successive measurements. Applying the Doppler shift to the radar equations yields the Lorentz transform. The graphic solution demonstrates the two postulates of the special theory. The invariance of physical processes such as clocks and rulers, because the two reference frames do not alter their orthogonality of the X and CT axes, nor change the units of measure. They are simply rotated with respect to each other. And it satisfies the invariance of the speed of light between the two reference frames. I hope you enjoyed this presentation and learned some things you didn't know about the special theory and the Lorentz transform. If you want to learn more, read my book, Writing on a Light Beam. You can purchase it on Amazon or via my website shown. Don't forget to press the like button. It helps to make this YouTube presentation more widely available. And thank you for watching.